Okay, so here we are again, and today we're going to wrap up chapter two at long last. This has been an incredibly important chapter, and although we're not completely done with derivatives by any means, but here's where we got a chance to learn definition of a derivative, and then learn all the rules that we'll need going forward. Today we have saved for last some of the more complicated rules, especially the one we're about to do, which is known as implicit differentiation. And but it is used for very specialized applications. And then we're also going to look at how to take derivatives for logarithmic and exponential functions. And if we have a little time, we may take a quick look at chapter three just to see where we're going. And then what I'd like to do is the next time we meet is have what amounts to a review session where we basically go back to chapter two and revisit all the rules that we learned and then do some problems that represent each of the different rules that we learned. So in other words, we could always use some more practice. That's the way I look at it. So anyway, let's take a look at chapter 2B, where we have implicit differentiation. Okay, now this one is very different. In a way, it's very different than what we've been doing, because here's the problem here that we're running up against. Normally, we have nice, straightforward functions. We have y as a function of x, which means we have an equation where y is on the left and all the x's and constants are on the right. And this is what we're used to seeing. But sometimes we run into a situation where that isn't what we have. Instead, we have a situation where, for whatever reason, the x's and the y's are mixed together in such a way that it would be very difficult or impossible to split them apart. And so when that happens, the techniques that we use to take the derivative are going to be a little bit different. Okay, now the rules of differentiation are still the same. What is going to be different here is that we will need to resort to the chain rule before we take any further steps. Okay, but we have to do it in a very specific way. So here's an example, what I mean, of a function that really would be difficult or impossible to break it down into all y's on the left-hand side and all x's on the right-hand side. So this would be a classic case when we would probably want to use implicit differentiation. Now, as is so often the case, it's not that we must use implicit differentiation, but chances are it'll be more straightforward than trying to do it directly. So let's just quickly remind ourselves, first of all, as far as the notation is concerned, the first derivative, f prime of x, can also be written in what's called differential form, dy dx. And if you recall, dy is an infinitesimally small change in y. And then this would, of course, be an infinitesimally small change in x. Okay. Now, you also will recall that we covered the chain rule earlier. And so what you're doing here is you're taking dy dx and rewriting it in an interesting way. We can rewrite it as dy du times du dx with the understanding that the y is itself a composite function of f and g of x. And we can then, in order to solve for this, we can write y as a function of u, and u itself can then be rewritten as a function of x. So if we choose the u carefully, that will make things simpler for us to calculate a derivative using the chain rule. For example, if we have a very messy polynomial raised to a very high exponent, we often find ourselves using the chain rule because expanding out the polynomial would take a very long time. And so, we usually have multiple ways of approaching any given problem. And of course, our goal is to always find the most direct way to get to our solution. So what does that have to do with this? Well, first of all, here's an example. Now, again, you could, in principle, split this up. If you wanted to, you could say, well, listen, this implies and then what you would find is that by taking the square root of both terms, both sides, actually got two expressions here for y. Y actually equals both of these. Okay, in other words, if you square both sides, you'll still end up with 25 minus x squared. So if you want to solve this directly by taking the derivative dy dx without using the chain rule or implicit differentiation, you could do it, but it'll probably be quicker and easier to simply use the implicit differentiation technique that we're about to look at. Also, if you recall, this is simply the equation of a circle centered at the origin with a radius of 5. Okay. Anyway, so why don't we find dy dx? So first things first. Now, of course, you know that we're allowed to apply any technique to both sides of an equation without affecting the results. So why don't we take the derivative of both sides with respect to x? Okay, great. Now, look what happens. On the right-hand side, this is easy because we end up with a 0. And what's going on here? Well, this will be on the next slide, but I just want to point out that in a case like this, what you've actually got is the derivative of x squared plus the derivative of y squared. Now, it's probably going to be a good idea to split them up like this because the dx squared is easy. We can do that with a power rule. It's the dy squared that will require us to use implicit differentiation. Okay, in other words, we're going to apply a chain rule to this in a very specific way. Not the way we're used to seeing. Okay, it's going to be a little bit different. So let's do it this way. We split it up. Okay, so we got the two terms. This is a breeze. We know the power rule very well by now. Okay. All right, so if f of x equals kx to the n, then f prime of x is nkx to the n minus 1, and this is our power rule. So here, with x squared, k would be 1. There's an implied 1 multiplying by x squared, and then n is 2. So nkx to the n minus 1 would be 2, 1, x to the 2 minus 1, or just 2x. Okay, great. So that's fine. Now, here's where we get into the interesting new material. What do we do with y squared? Okay, so now what it turns out that what we're about to do is write u as a function of y. Okay, so like I said, this is not what we've been doing previously. We were doing it this way. Remember, over here, u is a function of x and y is a function of u. What we're going to do here is change this slightly. And what we're going to do is let y be a function of, u be a function of y. And then that means that y must be a function of x. And so we have a composite function, which we can then apply the chain rule to. But now this is the traditional chain rule. Here we're rewriting it slightly because we're solving for du dx. Okay, why are we doing that? Because this is the function that we're actually applying this to. Algebraically, if you rearrange this, okay, so in other words, if dy dx equals dy du dx, if I divide both sides by dy du, that gives me dy dx times du dy. But we normally write it like this. Okay, I mean, this is correct. What I have here is fine, but we normally write it. The reason why we do that is so you can see that these actually are canceling each other out. So we have a slightly different version of the chain rule here, where we're solving for du dx with the assumption that u is a function of y. So in this case, Why not just let u be y squared? Okay. Now the power rule applies here, even though it's a y. That doesn't matter. The fact that the variable is y instead of x, the power rule still applies here. You would just write it a little differently. Like if you have f of y is k y to the n, f prime of y, which is let's see. Oh, let me not change. Let me leave it in the original form. Is going to be n a y to the n minus 1. And so remember before we saw that when we have x squared, its derivative is 2x because of the power rule. For the same reasoning, here we're going to have 2y. du dy is therefore 2y. Now we're going to plug that result in here. The du dy is here. Now, when you're done, that's what we have. Now, we don't have yet an expression for dy dx. Okay, so right now, as things stand, this is the result of taking the derivative of just y squared. So now we're going to combine all of these. Okay, so remember, we started out with x squared plus y squared is 25. Then we differentiated both sides with respect to x. This became 0. This one is 2x. And we just proved that this is 2y dy dx. And now we solve for dy dx algebraically. Okay, so we'll subtract this from both sides. And now we'll divide out both sides by 2y. Which then reduces to minus x over y. And if you notice, the answer is itself not even just strictly a function of x. We've got x and y mixed together, which is often happens when we run into these cases with the implicit differentiation. So that in a nutshell is what has to happen in order to use implicit differentiation. We're using a modified version of the chain rule to solve for dy dx. Now, it probably seems terrifying at this point, but once we've done it a few times, you'll see that it's fairly straightforward. I mean, it certainly still relies on the rules that we've been learning. So here's another one. Now you can see here's a mess. Although I must say, in this case, we could rearrange it algebraically and solve for y on the left and x on the right. But why don't we do it with implicit differentiation first, and then maybe we can go back and double check by doing that. Okay, so first things first. Now you always want to simplify whenever possible. So why don't we rewrite this as it isn't absolutely necessary. I just think it's easier to follow what's going along. So let's see. There we go. This is what I was after right here. Now, remember how now, by the way, this problem is more complicated than the previous one because if you notice, we have a product here, 3x squared y. The 3 isn't, and the 3 is a constant. That's not why we need to apply the product rule. In other words, we can rewrite it like this. But the fact that we have a product of two variables means that we must apply the product rule that we learned in order to solve for this problem. Okay, now here's the product rule that we learned before. Now, we're going to use the same logic, but the notation is a little different. So in other words, what I wanted to do is write it out in more in English terms. What are we actually doing here? If f of x is g of x times h of x, when you actually apply this product rule, you're taking the first term and the times the derivative of the second. And then you're adding to that the second term plus or times the derivative of the first term. We're going to do the same thing here with 3x squared y. Oh my God. Now, and by the way, don't forget, we're only at the moment solving for this 3x squared y. We'll save this one for later because it's very straightforward. So using that logic, given that this, so think of this as the first term, and this is the second term. So we'll have the first term. Now, the second term, the derivative of y with respect to x is just dy dx. Okay, we got lucky there. If it was y squared or something like that, then it would have gotten even messier. But since it's just plain old y, the derivative of y with respect to x is very simply dy dx. Now, what about this one? Y 6x. This is the second term. And of course, based on the power rule, this is the derivative of the first term. So that's the result of applying the product rule to this expression 3x squared y. So you can see it's still our old friend, the power rule. It's just that we've got a y mixed in there and we have to treat it very carefully. Now, the rest is pretty straightforward because you can see that's the left-hand side. The right-hand side is easy. Based on the power rule, the derivative of 10x, it's just 10. Okay. So what do we end up with? We have this expression, which we just figured out from the product rule. On the right-hand side, we have 10. Now it's just a question of rearranging this algebraically to solve for dy dx. So we get all the non-dy dx terms on the right-hand side. If you notice, I rewrote that as 6xy. That's pretty standard. When you have x's and y's mixed together, you tend to write all the different x's first in decreasing order of exponent. Then you can do all the y's. Alphabetically, x becomes before y. So this is pretty much what we're used to seeing. Now, all I have to do is divide out both sides by that 3x squared, and I'm done. Okay, now, what we're going to do is something interesting here. We're going to go back to the original equation and say, listen, was there another option here? And the answer is yes. Okay. What if we'd done this? Looked at it and said, this looks like a catastrophe waiting to happen. What we have here is a golden opportunity to use the quotient rule. Okay, so let's see what would have happened. So remember the quotient rule, if f of x equals g of x over h of x, we're going to have this. Okay, so in our case, we have 10 over 3x. Which is helpful because, as you know, the derivative of a constant is 0. And according to the power rule, the derivative of 3x is simply 3. So this won't be a very complicated expression. We'll have 3x times 0 minus 10 times 3. Okay, so that leaves us with negative 30 with 3x where the entire expression is squared. Okay. So that's that. Now, if you notice, it doesn't look like this, does it? What happened? Okay. So you might say, well, wait a minute, that can't be right. But remember, we did determine that y equals 10x over 3x squared. So what I'm going to do now is this. We'll take this result and say, you know what? That doesn't appear to match what we got here, does it? But if you replace y, actually, I'm going to need the next slide for this. Hold on. I'm running desperately short on space. So here's what we have when we use the quotient rule. And here's what we got for dy dx, that is. 10 minus 6xy over 3x squared. The understanding, remember that we determined that y equals, from the original equation, 10 over 3x. So here's what we're going to do. I'm going to substitute this expression for y, and let's see what happens. Okay, so just as a side note here, this gives me 60x over 3x, which is 20. So I'm actually subtracting 20. Oh, you know what I just realized? I think I copied something wrong here. No, you know what I did? I didn't reduce it. I was just, for a second there, I was nervous. It just suddenly dawned on me that this is equal to minus 10 over 3x squared. I should have reduced it. Okay. That makes things a lot simpler. Okay, that's better. Anyway, so you can see what's happening out now. We end up with the same thing. So basically, all we did here was demonstrate that by doing this with implicit differentiation, we get the same result. It's just that it's expressed in a different way. Now, it's not always possible to do this or not practical, but it's nice when we can double check our results. All right. So this one, yeah, we definitely need to practice with this one. This is a difficult concept, implicit differentiation. But again, it's all about combining the chain rule with the rules of differentiation. Okay, so when we do our review session, we'll make sure there's plenty of these in there. All right, now let's go on to the next one. Now, these are much, much more straightforward by comparison. The derivatives of exponential functions and logarithmic functions. So E, of course, is approximately equal to 2.71828. And we will see it quite often in fields like finance, where we're trying to calculate how much a sum of money will be worth in the future, for example. It's a very useful concept. So now and by the way, this is going to come up later on anyway. I might as well show it to you now. It's a limit, okay? It'll show up in a later chapter, but I just wanted to throw it out there now. We'll see that E is itself simply a limit. Okay, so anyway, once that's said, now watch how simple this is. Look at this. If f of x is e to the x power, f prime of x is just e to the x. Well, that's the simplest derivative you'll ever see in your life. Okay. Um, Now, if the exponent is a function of x other than just plain x, using the chain rule, and this is coming from the chain rule, by the way, then what we have to do is it's instead of just e to the g of x, we need this g prime of x. And by the way, this is just a special case of the chain rule. Because look what happens if you take this and write it as e to the x times g prime of x, that's just one. So that's why it's so simple. It is technically derived by using the chain rule. It's just that g prime of x in that case is one. So we end up with e to the x. For every other case, we need this g prime of x. So for example, if our original function is e to the 3x, then g of x is 3x by the power rule. G prime is 3. And then we end up with e to the 3x times 3, which we, of course, will rewrite as 3e to the 3x. It's just a convention. You don't have to. You can leave it like this, but it's not normally done that way because this 3 is clearly the coefficient of this expression. Now this one is you might not think so, but this one is a little bit messier because the g of x itself is not such a simple function of x. So now, by the way, as is often the case, every one of these can be solved at least in two different ways. So if you use the chain rule, let me write it like this. Now you've got this 3 here. So what you end up with here is g of x is x squared. G prime of x based on the power rule is 2x. So you've got e to the 3e. Now the 3, by the way, the 3 can be factored out from what we're about to do. So you can put a 3 on the outside and then apply the chain rule just to e to the x squared, and you're going to get e to the x squared times 2x. And then you can multiply the 3. You end up with 6x e to the x squared. So you can see it is a bit messier. But if you really were determined, you can avoid the chain rule altogether by using the product rule. But if you're going to do that, that means this is your g of x and this is your h of x. Now, I would say that in a case like this, it's probably just as easy to use the chain rule. But if you want to do it this way, that's fine. Because g of x is 3. H prime of x would be 2x. And then, oops, I wrote the wrong thing. Sorry. This would be e to the x squared. Okay. So you've got, I did something wrong. G of x, h prime of x is e. Oh, okay. See, now uh, you end up using the chain rule anyway. So this really doesn't make a whole lot of sense. Now, this is ridiculous. No, I don't know. I mean, yes, it's nice to know that you could do it both ways, but I really think that you're probably better off just doing the chain rule because you needed it anyway. As you can see, in order to solve for h prime of x, we did need the chain rule. So I think our best bet is to stick with the original, the chain rule, that is. Now, what about this one? Now, this one is kind of a disaster. I think here it's probably a good move to use the quotient rule, but even then, we're going to need the chain rule to determine the value of g prime of x. So in other words, this is g of x, and this is h of x. And so g prime of x will be this function times the derivative of this new exponent. Okay, so e to the g of x, remember, let me just write it down one more time. If your function is e to the g of x, f prime of x will be e to the g of x, g prime of x. Okay, the denominator is easy. H of x is x, h prime of x is just 1. And then you just plug them into the quotient rule, which is, yes, it's a very complex formula. So everything is laid out for you here. And we plug them in. Now, often these end up giving us a very messy result. If you can reduce it, that's fine. Okay, you go ahead and do that. But here, that isn't really the case. Although I suppose you could write this as, of course, they mean the same thing. That doesn't really make it that much more simple, but there's no possibility of anything dropping out, no factoring. So we'll leave it like this. So the bottom line is, where was it? Right here. This is what we're taking away from this section. That's the heart soul of all of these. Whether you choose to use the multiplication rule, or product rule rather, or the quotient rule, or if you're just applying the chain rule directly, this is what you have to remember. The part that's easy to forget is right here. Okay. That's the part that you could make a mistake and forget about it. So if there's a rule for exponential functions, there must be another rule for natural logarithms. And of course there is. How does it work with logs? Well, first of all, don't forget logs are only defined for strictly positive x's. The log of 0 is undefined. Anything between 0 and 1, the log is negative. So if you recall, ln x, natural log of x, looks something like this. Vertical axis acts as an asymptote because the function will never quite reach 0. Well, here's the derivative of just plain log x. If f of x is log of x, f prime of x is 1 over x. Now, of course, if it's the log of something else, of course, there's going to be a chain rule involved. And what would that give us? Aha. Okay. So if we're looking at log of g of x, then the derivative is could be written in a couple of equivalent ways. G prime of x over g of x. Okay. So this is one of those cases where it's probably worth your while to memorize this. The rule for exponential functions right here, and the rule for logarithmic functions right here. By the way, there is a separate rule for other logs besides the natural log. What happens is you'll end up with another term in here, which is another log. So we will get to that case, but for natural logs, this is all we need. For the others, like log 10, for example, there'll be another term in here based on log 10. All right, so here we go. So log of this whole expression is g of x. And then, because it's a polynomial g of x, all we have to do is apply the power rule to each individual term. Okay, so g prime of x is very simply 3x squared. Then we have 3. And then, of course, the derivative of a constant would just be 0. So all we end up with is 3x squared plus 3. So this ratio, g prime of x over g of x, is now just 3x squared plus 3 over x cubed plus 3x minus 4. And, again, if simplification is possible, you might want to look into it. But if not, you may as well just leave it the way it is. Sometimes you get lucky and every term has an x in it. We can cancel them out or factor them out. If not, then just we leave it like this. All right, let's try another. Oh, now you can see what's coming here. Um, you could rewrite this. Now, g of x is this expression. The problem here is that g prime of x is going to be a nightmare. Okay. So it turns out that sometimes we can simplify our results by taking advantage of the properties of logarithms. So in other words, watch what we can do. You might recall that the log of x over y, no matter what the base is, it could be any base, it's not just the natural log, is equal to so that should give you a hint as to where we're going with this. We're going to avoid a messy quotient rule by doing this. In fact, oh, look at this. How very clever. Since there's a product here, we can avoid, we would have, oh my God. If we did this with a quotient rule, we also would have needed the product rule. So here we can split it up into 3 terms. And I think you'll agree this will be a lot quicker. So for this first one, g of x is x squared. Based on the power rule, g prime of x is 2x. Now, the derivatives of trig functions, you don't really have to memorize them, but you might at the very least want to have a chart in front of you that shows them all when you're doing these problems. Because, after a while, you'll have a few of them memorized, but like here, for example, you might recall that the derivative of sine x is the cosine of x. And then this last one, g of x is the 2x plus 1, which means that g prime of x based on the power rule is just 2. So remember, each one of these terms is g prime of x over g of x. And we're done. I think you'll agree that wasn't very painful at all. So, when you see an opportunity to simplify like this, you really should go for it because doing it the straightforward way, meaning just go ahead and use the quotient rule combined with the product rule, it would have been a lot messier. All right. By the way, this is, you'll see as we go along that we sometimes simplify horrifically complex equations by applying logs to both sides and using these amazing properties because they really can simplify some truly terrifying equations. Oh, now here's one. Now remember how this works. You have an exponent like that, the log of x to the n power is equal to n log x. So again, we're using the properties to make this simpler. Okay, so we're going to rewrite this as 5 log 3x plus 2. Now, the 5 is simply a constant. So what ends up happening here is that we can think of this. We can keep the 5 in the outside of whatever we're doing. And here, this means that g of x is 3x plus 2. G prime of x would just be 3. So here we have g prime of x, we have g of x. The 5 stays on the outside of this, and we end up with this result. Wow. So again, we basically saved ourselves a lot of potential grief by using the logarithmic properties, especially when there's exponents involved. All right. Now, what about the other logs? I started to mention this before. Log 10, log 2, whatever it is. Um, this requires, the calculations are slightly more complicated, not much. So here's how it works. For the log of any given base b of x, okay, so instead, remember before, derivative was 1 over x. So what they're saying here is that for any given base b, you've got 1 over x log b. And that means that this is a special case of this rule that you're looking at, because with the natural log, oh, what did I do? Sorry, this is supposed to say log x. Okay, that's better. Why don't we rewrite this as log e of x, because that's what it is. And then this is telling us that we have 1 over x natural log of e, but this is equal to 1. So in other words, this very simple rule is a special case of the general rule for any log for any base b. Okay, so that means that if we're taking the log not of x, but g of x, you can see, and we have this extra term instead of just g prime of x over g of x. Okay. Not only that, oh my God, now look how interesting this is. If we have b to the x power, then the derivative is b to the x times log of b. So if we had, for example, wow. Okay, so you can see um, that's a pretty straightforward rule. And if we extend this to b to the g of x power, rather than just plain x, g of x, what ends up happening there? Ah, well, it does get a little messier, right? Let me copy this here so you can see them side by side. So if we have f of x is b to the x, And then the derivative becomes this. Oops. Okay. So what happens when we change that to b to the g of x power? It's b to the g of x log b. So in other words, this is the new part because this could have been written as b to the g of x log b, and then all of a sudden here's this g prime of x. So that's the complication that comes about because it's g of x instead of just plain x. Oh my God. Yes. Now, of course, you can see this is a special case because here you're assuming that g of x is x and g prime of x would just be one. So that's why you don't see that g prime of x in there. But I mean, it's implicitly there. We just don't need to write it. This is the general approach. All right, here's a good example of this. Log 3 of x. Okay, so let's use our rules. Oops, wrong rules. No, 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 sorry. Let's go back here. So if we have log base b of x, then the derivative is here. So here, this is our b, tells us that we're going to have 1 over x log b, which means it's very simply 1 over x log 3. Okay, now let's try another one. Okay, now this one means that we have, instead of simply x, we have g of x. Let's go grab that case. Okay, so here the b is 5, g of x is here, and we can apply the power rule to each term separately to come up with g prime of x, as you can see down here. So we're going to have the ratio of this g prime of x over g of x, the original g of x, times the log of 5. Uh-huh. So here we go. Now we're looking at the exponential cases. So let's look at these. B to the x. No, no. There we go. Okay, so clearly here the b is 3. This rule tells us that you'll have the original 3 to the x times the log of b. Okay. Now we need an example where the exponent is some kind of a function. Oh, there's no more examples. Oh, wait, here's one. The- It's just being slow. I knew there had to be. Here we go. Very good. All right. So let's go back and grab the rule. All right. So this is how it works. So here's our g of x, and here's our b. And of course, again, based on the power rule, g prime of x would simply be 6x squared. So when we plug these in, we have our b to the g of x. We have g prime of x and ln b. So we basically, what we've done here is we introduce rules for exponential functions and for logarithmic functions. In both cases, we have a rule for when we have x, and then when we have a full function of x. Okay, so keep in mind when we use just x, it's a special case of g of x. So I don't know if there's a table in the book that summarizes all of these. What you could do is make up a chart yourself. In fact, why don't we do that right now? I like it. I like having tables. Um, it's for things that are hard to memorize. Why not? So let's just copy these. We'll put the original function and then the derivative. So this is when it's the log for any base of b. And then when we have the log of g of x, we'll end up with this is our derivative. All right. And then for the exponentials, we have, here we go. Let me just make this a little bigger. By the way, if you're wondering about the differences in the font, these were created with a product called MathType. It's an equation editor that once upon a time was actually part of Microsoft Word and PowerPoint. Now you have to pay for it yourself, but it's worth it. It's not that expensive. And you can see it's really a very high-powered professional math editor, which I obviously have to do this stuff. But sometimes, if you can just type it directly, you can do that too. Um, the problem here is that these sometimes don't show up properly on a Mac. That's the thing. The Mac type isn't compatible with the Mac. So that's why, you have to be careful. And of course, if you really know what you're doing, there's something out there called LaTeX, which it really is a uber powerful system, but it takes a long time to learn it. All right, here we go. Okay, and then there's just the one more. when we have b to the g of x. Yeah, here we go. Okay, so now they're all together in one place. So hopefully this will come in helpful because it's you could memorize these and you probably should think about it, but um oh no, I just realized I copied something wrong. Sorry, hold on. No, this is wrong. Now we're good. Okay. All right. So those are the four basic rules. And just remember for the one on top, if you have a natural log, the b is replaced with e, and this just reduces to 1 over x. So they're all together in one place. But I think you'll agree these are very straightforward rules. You might have to, remember them, but it's the chain rule is different. The chain rule is a very complex process. And so implicit differentiation is it can get very, very messy. So what I would like to do, like I said, is set up a bunch of practice problems. Um, and I'll try to cover all the different rules that we learned, and just so you can see one more time how this works. And then you should be completely ready for the assignments for chapter 2. And then, like I said, chapter 3 is a pretty long chapter. There's a lot of incredibly important topics in there. And it gets a little bit more theoretical. Um, I mean, if you look at all the things we have to do, we're going to start thinking in terms of optimization, which means finding maximum and minimum points. But unlike what we did earlier, we're going to find them with derivatives. Okay. And you'll see that that makes it much more simple than what we had to go through before. And we also will be learning how derivatives tie together with limits. There are certain types of problems we may encounter where we can simplify our results with derivatives. And then we have, well, you'll see when we get there. Optimization, which means we're trying to find the highest or lowest value, that type of thing. Like in economics, you might be trying to figure out the maximum profit you can earn, or you can figure out the minimum cost and that type of thing. So this is a fairly involved chapter. So, but first we'll have some reviewing, and then we'll get back to this after that. All right. So I guess we'll stop right here, and then I'll see you next time.